Alright, what we're looking at here is collisions. And again, this is year 12 work. If we have a ball moving along, say we'll make that one 2 kgs, we'll make that one 4 kgs, and that one's not moving, and that one is. And we'll make that 2 meters per second. We're going to have a collision, right? Now, if we are wanting to look at this collision, and we know it's a isolated system, again, no external forces operating on the system, then we know that we're going to get conservation of momentum. All right? Remember the principle, no external force, conservation of momentum. Now, that means that the total momentum after must equal total momentum before. Now, we could do this with 100 different particles or masses, and we'd have to add up all their momentums before and all their momentums after. So that little diagram I showed you where we had a whole bunch of little guys racing around, you may not have seen that video, but you will. Then we could do the same thing. Again, isolated system, no external forces. Now, the thing is, if this guy is the only one with the velocity, then the total momentum before, this is before, is just going to be equal to 8, and momentum mv, kilogram meters per second, right? Because that one's 0. We haven't forgotten about it. So that is the same as afterwards. If our coordinates are positive to the right, then because his velocity is to the right, remember momentum is actually a vector, then we could draw that as a vector like that, 8. And that's what the vector's got to be like afterwards. So after the collision, if I tell you that the 2 kg one is going at a 45-degree angle like this, and that was his momentum, so this is, if we call that ball A and we call that ball B, then if I tell you that B is doing that, that's his momentum for B, this is all after, then you know that the other ball, you've got this total momentum that you know the collision afterwards, the balls must add up to. So you now know that total momentum requires that the momentum of B afterwards, A afterwards, be that vector, because they've got to now add up to a vector that's 8 and totally horizontal there. Now you can do this just with these little arrows, these little vectors. So now we've got the momentum afterwards for that guy. Now, if you want to look at change in momentum, right? So change in momentum for ball B. Well, ball B had a momentum that started off as 0. So that was initial momentum for ball B. Ball B's final momentum was like that. We call that 45 if we like. So change, as you should be aware by now, is equal to final minus initial. Now when you subtract a vector, you just put the arrow on the other end. So final we've said is that. Alright? So change in momentum is final minus initial, which is just that. So the final is that, minus the initial is 0. So that's change in momentum for B. It's actually the same as final momentum since we didn't have an initial momentum. But have a look at A, change in momentum for A. We've said that A started with a momentum like this, 8. So that's A's initial momentum. And we said A's final momentum was like that. So if now we do final minus initial, let's just move that up a little bit, then we get the final, and we get the initial. We had to reverse the initial, and we come to a vector like that. So that's change in momentum for A. Notice something. Change in momentum for A is equal and opposite for change in momentum for B. So delta P for A is equal to the minus delta P for B. That makes sense because we're saying the total momentum is going to stay the same. So if one gets 6 more in the positive direction, the other one must have 6 less in the negative direction for the total momentum not to change. Right? Now the other thing is this. Remember this? Impulse. We said that force times delta t equals delta p. So change in momentum is equal to force times delta t, right? So if the change in momentum is equal to F times delta t, then if you've got a momentum or a change in momentum like that, right, if that's your change in momentum, then if you divide that change in momentum from delta t, then you've actually got the force. So the force is always in the direction of the change in momentum. Of delta p. So the force is in the direction of delta p, but we said delta p for A is equal to negative delta p for B. We've said they have equal and opposite changes in momentum. So they must have equal and opposite forces. Equal and opposite forces in that collision. That's Newton's third law. Remember Newton's third law? If you've got a force on A, then you've got an equal and opposite force on B. They're not on the same object. So this is what we needed to know a little bit about collisions.